Okay guys, here we are, it's Monday, so we're going to move on to more of the quantitative type descriptions rather than the categorical that we did to end last week. So we're going to start with how to describe a distribution for quantitative and then a couple of quantitative graphs. So here we go. We'll start this slideshow. And we're just going to be looking at graphs of quantitative data, but it's not enough just to graph them. We have to be able to describe them too. What we need to do is to kind of hit on what the overall pattern is that we see within that graph, and anything that is important as far as a deviation goes from whatever pattern we see in it. And a good way to follow along and to remember what to look for is this acronym SOCS, S-O-C-S, shape, odd characteristics, center, and spread. If you can remember that and figure out from the acronym what the four things are we're supposed to comment on, that'll help us to make sure we do comment on it. Because if we don't comment on it, for the AP people, they don't like that. So that's what we need, SOCS. So we'll start out with the S there, and that would be shape. And there are just an endless variety of shapes, but there are three that we're really going to be looking for specifically. There's symmetrical, there's skewed, and there's bimodal. So looking at those, we'll start out with symmetric. Those further break down into two different types. There are uniform distributions, where the values occur with approximately equal frequency. I mean, picture my paycheck. I just get the same amount week after week after week after week after week. So if I were to graph that, it would start kind of right on the x-axis, shoot up to whatever it is that I bring home, and then stay flat like that. It will form a distribution that looks like a rectangle. So uniform distributions. Bell-shaped distributions look like, shockingly enough, a bell, or better yet, a mound. A bell is a little bit too perfect, and we're just looking at distributions of data which are not perfect. They're not ideal, so they're going to carry some variation that we see within the data, and so it will deviate from being perfect. But anything that can roughly fit into a bell shape or a mound shape, that would be a bell-shaped distribution. Now, normal distribution is the ideal of that, and I don't know that we're ready quite to call those things normal. Bell or mound would be fine. So looking at this is a histogram, and we'll cover this in a few days. It's shaped kind of like a bell. So let me go ahead and get the shape emphasized for you. Let's see if I can make sure this works. Okay, come on now, here we go. All right, and it just goes up and comes back down. And so there's your bell. I know it's got some irregular detail, but that's sort of the way these things are. They've just got the irregular detail, and I didn't mean to go ahead. I just meant to get rid of the pen. But if we just kind of smooth everything out, the bell will reveal itself. Okay, uniform. Now this does not look like a rectangle, but we've got some irregular behavior up here at the peaks. That's just the kind of what we would see in data. It's never going to be perfect, as I said before. So if we can just sort of generally fit a rectangle to it, like so. There you go. That's uniform. All right, let me get rid of this. Just a moment. There we go. When we leave the symmetric distributions, we're going to see things kind of go off into like a tail, where there's a lot of observations on one end and very few on the other, and it kind of creates sort of a slide looking thing, like a tail. And it's going to stretch out. It'll either stretch out left or right, and within the tail will be a few, unusually high or unusually low values that are sort of away from the overall amount of the distribution. So it can be skewed left or right. And so let's look at some of these. All right, so here's test scores, and this is actually a perfect example. Some test scores are norm reference. Their distributions look like bells, but many of the ones you're familiar with, like tax, star, anything like that, you typically will get people that'll score a lot on the high end and do well on it, and then we have a few that don't score so well. So if you can fit this kind of a curve to it, you can see you climb up the slide and then slide off to the left. That is where we get skewed left from. Likewise, we can also have skewed to the right. So let's look at that. All right, here's one that's skewed to the right. I'll just draw that out for you. Got to get my pen back. And so up it goes. Up, 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 and then that's skewed to the left. It might dip down a little more, but you get the idea. I'm not sure about the populations that they're talking about here, but an even better distribution that you can always count on to be skewed to the right would be incomes, because here are where all the Bill Gateses are, and the very few that there are, and here's where the rest of us are. It's kind of normal in this country. Incomes are skewed to the right. And that has big implications for number summaries like mean, median, and mode and that kind of thing. All right, so bimodal. All right, this is when your data has two separate high points. I mean, really distinct, not just irregular data that kind of makes little bitty peaks. These are going to be very obvious. When you see this in some kind of a graph distribution, they usually represent two populations. If you have more than two, we can call it multimodal. All right, this is bimodal. It's clearly bimodal. It doesn't really say what it is. It's not well labeled, but we're not too concerned about it. So see, it kind of goes up and then swings back down dramatically, goes back up, and then down again. What you normally can imagine is going on in a case like this, let's just say I want to get the heights for all the seniors in Cinco Ranch High School. So I measure them, and oddly enough, I get this kind of a bimodal distribution. Well, maybe it's because I've got two populations mixed together. Now, I know that this is not always a true case, true thing case by case by case, but I think it could be pretty much assumed that the guys are somewhat on average bigger or taller than the girls are. I mean, we got some real short guys and some real tall girls, but in general, if you mix up the populations and you see that that trend is there, you will see it in a bimodal graph such as this. All right, I guess we're on the arrow. Okay, so the O is for odd characteristics. So anytime you see a gap where there's just an empty spot with no data, outliers, clusters, these would be considered to be odd, and they should be reported. And you should ask yourself, what are they doing there? Maybe they shouldn't be there, or maybe they should. This depends. See the gap? This looks like three observations. You could say there's three outliers on the low end. You could say there's a cluster here and a cluster here. You can say there's a gap between 2.625 and 3. So, however you want to say it, just any of those should work. Center. Now there's a couple of ways to measure center. We're a little bit early to be dealing with that. We're going to be looking today just at the median, and you'll recall from earlier math classes that if you take data in a data set and you rank order it, say from least to greatest, that the exact middle of it will be the median. Now, if it's an odd number data set, that middle number is the median. If it's an even number data set, then it splits exactly in half and there is no middle number. And you'll recall you take the two numbers to either side of that split and average them. There's actually more complicated than that. We'll pick up on that a few days from now. But again, for an even number data set, that's how you would determine the median, as you probably remember. Spread, this is a little bit tricky too. I'm going to introduce it with something that's kind of crude, kind of not used, but it's easy to understand. Right? Range of the data is the difference between the maximum or your highest data value, the biggest one, minus your smallest one. That's your range. So if I give a test and my highest score is 100 and my lowest score is a 70, that gives me a range of 30. Now, if I ask you what the range of a data set, don't just tell me it's max minus min. I know that. You actually have to plug in a number for the max, plug in a number for the min, and then give me a single number for the difference. So please don't just regurgitate the formula. I know the formula. We just need a working number. Now, this is fine, and it does communicate, but what if somebody comes in who was absent and makes a 10? So now all of a sudden my max is 100, my minimum is 10, and the range shoots from 30 to 90 just because of one weird test score. So that can sometimes make the range a pretty non-representative value for your data set. We have better ways to measure spread. Yeah, don't use range too much. It's very crude, and so it's used sparingly. Okay, this is your attendance code. Let's go ahead and pause. You can dive into Canvas, find today's date, and just enter that, submit it, and then we'll come back. All right, we got the attendance out of the way, so let's move on. We're going to look at two types of quantitative graphs. These are very basic kinds. They're not really good for professional use, but they're good field graphs. Dot plots, stem plots. We use them for small data sets, and we want the numbers to be discrete in nature. If they're not discrete, then too many decimal places, they're going to be too hard to graph. If you're starting to graph and you're using one of these two and it's just not going well, you need to try something else. So a histogram would probably be a better option. We will learn about those, I think, tomorrow. All right, so here are the Kentucky Derby winning times. This may be a little bit more data than we want. I think I looked it up. It's between 1875 and 2011. You find your lowest value. You start your axis either there or just a little below your highest value. End it there and put a decent scale on here. Put a label, a title, and just start piling up the values. So all of the 120, these are in seconds, go right here. So the first one went here, the next one's above it, and then above it, and then above it, and then above it, and so on. All right, so you get some kind of idea of frequency, and you just keep doing that until you've covered all the values. Unless there's some years missing, there should be 136 of those dots. That may be a little bit high as far as for dot plots are concerned, but I suppose we'll deal with it and we'll let it work. All right, it says we can display it horizontally or vertically. I kind of like them horizontally. So let's go with socks and figure this out. So shape, skewed to the right, I would say slides off to the right. Unusual characteristics, it looks like these are scaled by 2, like 132, 134. So we have a gap between 134 seconds and 154 seconds. Yeah, okay. So let's see, C would be next, would be center. Okay, this one's going to be hard. We've only got the median so far. If you have 130, what did I say, 136 of these, all right, that's going to give us a median, well, 68 below and 68 above. You can actually count 68 values and find then the 69th and average the 68 and the 69th. I don't know what that is, but you can actually count the median in a case like this. And then spread, well, let's see, 174, that would be 54, and then we'd go down 2 more, so that would be 56 for the range. All right, there's better things that we can use, but for right now, that's all we've got. So there it is. Use seconds. If I did not say seconds enough, we always want to include units. The AP people really like it if you do it, and they really don't if you don't. Okay, so example, test scores. These are just a bunch of test scores, and let's see what it would look like in a dot plot. Now I want to kind of get out of here, at least for the moment, and I want to show two calculators. So we'll start out with the NSpire, because that's usually what most people have. And so here's what I did. I opened up a spreadsheet and I titled it. It's always good to have a variable name here, and then I typed in all of those values. Now this is actually, we can do a dot plot with a TI NSpire, but the major thing we want to do here is we want to sort. So what I would do is just go all the way up and just select the whole column, and then go to Menu and Actions and Sort. See, sort is choice 6, so Menu, Actions, Sort. And this is column A, so we don't really need to type in the scores. Ascending is least to greatest, going down. Descending, if we want that, is from greatest to least. You can do it either way. I'm just going to do it with, let's see, with ascending, and I'm just going to hit OK. And now it's all in order, so that makes it easier. I don't have to jump around and lose where I am as I plot these things, okay? So that's one kind of thing, and that's one kind of type of calculator, and that's how we do a sort on the NSpire. If you have a TI-84, that would be here, and I went ahead and let's turn it on. And let's just say you're in the home screen, and so that would be, let's see, second mode to quit. Just go ahead and hit Stats, and then Edit, and you can edit all of your lists. See, I put the same values here. You don't necessarily name it for these calculators, but what you can do is go back to Stats, and you can do Sort Ascending. So we can do Sort Ascending, and that was in list L1. So we can do second, and L1 is right above this number 1 key in blue. So we'll sort L1 and hit enter. It says done. Let's check. So stat edit, all sorted. Okay, good deal. So what I want to do is go back to the NSpire and go home and show you that you can actually plot one of these things. So let's go to here. This is a stats graph. We're going to use both of the spreadsheet and the stats graph a lot. And it just gives you this amorphous looking thing. If you click to add a variable, we're going to add the only one we've got, which is scores. And now the only thing it's missing is a title. So we can talk about this. It looks like it's skewed to the left. And now look, it looks like you've got a gap here, but you're only missing one value. You can mention the gap if you really must, but it becomes a an idea of just sort of detail, just maybe extraneous detail when it gets to be that small of a gap. But in general, I would just say this is skewed to the left, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we'll count 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. The median is 94. Spread is 97 minus 88. That would be your range, would be 9. Test score units. So there you go. You can do that on your NSpire. You cannot do this graph on a TI-84. But you can do it by hand. So if you do it by hand, it's going to look like this. Now I probably should have put scores here, but it did seem to be a little extraneous. So there it is. Just draw a line, cut it up into a scale, put some values here. Don't go down to 0. Why bother, right? You could have probably started at 88 and ended at 87 or 97, but that's fine. Okay? So let's go on. And where were we? Okay, we were here. Now, stem and leaf graphs are a little bit different. They're going to show the distribution of a quantitative variable like histograms do, and we'll get to histograms, but you'll be able to see, or it preserves the individual values. You'll see the data. You can recover the data just by looking at it. It's going to satisfy your area principle when you show the distribution. So let's see what we have next. All right, so constructing one of these things. Okay, first you cut each data value into leading digits, stems, and trailing digits, leaves. So it's called a stem and leaf display. You use the stems as a bin label, and you use only one digit for each leaf. So if it's 124, 1, 2 is the stem, and the 4 is the leaf. You have 56, 5 is the stem, 6 is the leaf. All right. If your data is, got extra detail in it, like 56.2 or 56.8, just round the one to 56 and the other to 57. You don't want all that extra detail. It's not going to change what your graph has. So don't forget a key or a legend. All of this doesn't really make much sense until you see one. All right, so here are scores on a psychological test. And you can put them in your calculator and sort them to make it a little easier to handle. But we'll go back and look at what it should look like. So let's go down to the next screen down here. Okay, so scores on a psychological test, and there's your title, and there's your legend. All right, your smallest score was 103, and you also had a 109. So there's 1, 0 for the stem, and then a 3, that's 103, and then 1, 0, and then the next leaf is 9, so that's 109. So you can recover the 103 and the 109. The next value was 115. So 1, 1 for the stem, and 5 for the leaf, and it goes all the way up to 9, and then you start in the 120s. So you have a 126, a 126, and a 129, a 137, a 137, a 140, and so on. Now, a couple of things. You need the legend. That way your reader can look at this and go, oh, okay, that's 129, and that's 178. So you've got to have your key or legend. Right, the other thing is, if you feel like you start in the 100s and end in the 200s, but you're missing values, like there are no 180s and no 190s, don't leave those out. Okay, if you don't have values, no leaves for particular stems, you need them in there. If you take them out, then this moves up and you lose the gap. Okay, so let's see. Let's rotate the view and let's go counterclockwise. And now you can read it. It's a little skewed to the right, and the reason that you have these two values here, these are outliers, more or less, or at least there's a gap here. So if you have that, these are extreme values, that means you've got to skew to the right hand, all right? Don't tell me it's bimodal. This is not enough of a dip for it to be bimodal. Don't get crazy with it. This is going to be skewed to the right. Figure out the median, figure out the range, and center, and then mention the gap here, and you should be good to go. Okay, so yeah, don't get carried away. This is basically skewed to the right. All right, so let me see what the next one, if I need to rotate this. Yeah, let me just go ahead and see if I can't rotate. I need clockwise. Okay, so let's see what we've got here. Let's go back to here. All right, scores on a French quiz. Now here's the thing about a stem plot. You really need to have like 6 stems. Here we go from, I think, a low of 10 to a high value in the 30s. So that would be your 10s, 20s, and 30s. That's only 3. That's not enough, all right? So what do you do if your data looks like this? So let's go back and look at how I drew this out, because we may be able to find out what the answer is. All right, what you need to do is to split your stems. Okay, so This first one in the tens goes all the way up from 0 to 4, and the only one I have there is a 0. The next one, your leaves go from 5 to 9. So that's 15, but there aren't any. So this one goes, these stems, leaves rather, go from 0 to 4, and these go from 5 to 9. See how we've spread those out a little bit more? So this is 20, 20, 22, 23, and so on. This is 25, 29. Instead of just piling this up here, then we can get a little bit more detail out of it. We did the same thing. Now I did an extra 3 here. I left it blank because there was nothing above 33. The only reason I did that was so that the reader didn't look at it and go, well, there's 2 1s, 2 2s, but only 1 3. Okay, so it was just to keep the reader informed as to what was going on. There's my key, there's my title, and when we rotate this thing, let's see, we'll rotate counterclockwise. All right, this thing is skewed to the left. Now don't start saying it's bimodal, okay? Because we split the stems and added the detail here. If I piled this back up on here, then you would not see that sort of bimodality here. This is just going to be skewed to the left. And you can count the median and let's see, center, unusual characteristics. There really aren't any. Shape, we covered that. And the spread is from 33 to 10, so that would be 23 for the range. All right, does that make sense? So let's rotate that back and let's see what else we've got stuck away. All right, now this says your homework. This is the dot plots, stem plots, and histogram worksheet 1 through 5, but I just want to show you one other thing that I've got here before I sign off. And let's see, it's on here. And the question is, so this was the original scores on the French test, but what if you got your data like this? Well, you're getting an extra digit here, and that's it's discrete to the 10th place, but I mean, you're gonna have to have just crazy stems and leaves to just leave the decimal as the leaves. So that would make things more complicated. Don't mess with that. Just round this more or less back to this. You'll get the same information that you would have had if you hadn't rounded, and you'll be able to handle the data in this format. So if you need to round, do it. You will not lose information about shape, clusters, outliers, and you can do the range from your original data if you want to, but all we need is a quick snapshot and some idea of what's going on here. Okay, I've had you for enough time, so I'm going to cut you loose. I've given you your assignment, so go for it, and I will see you next time.